In finance, the rule of 69 is a method for estimating an investment's doubling time. So if I invest $100, how long does it take for that investment to now be worth $200? So using the compound interest rate of R%, the time it takes to double your investment is given by the compound interest formula 2, because we're doubling, 1 plus R over 100, because percents are measured out of 100, to the power t. Okay, so that's the formula. You would rearrange this and solve for t. Okay. We're being asked, using the knowledge that ln 2 is 0.693147 approximately, justify the approximation that instead of rearranging and solving for t, you could just say, well, t is 69 divided by whatever the rate is. And this is a real financial approximation that people do use. It's got variations, rule of 72, rule of 70, but yeah, it's a real thing. So what can we do? Well, we've got to sort of start with the formula that actually computes t. Currently, it is not set up to solve for t, but we can change that. Apply the natural logarithm to both sides. That t can hop out. And then rearranging to solve for t. T is ln 2, which in the question they give me an approximation for. And then all divided by ln 1 plus r over 100. You might say, hey, I know an approximation for ln 1 plus x. We know the power series for it. And so we could approximate it by just using some Taylor polynomials. Right? We could use t1 or t2 or something like that, and that would be a useful approximation. Now we're told ln 2 is about 0.693. I'm just going to use the approximately 0.69 in place of my ln 2. Now why am I doing that? Well, I notice I need to get a 69 here. I see a 6 and a 9 very clearly with the ln 2. But how do you go from 0.69 to 69? You'd have to multiply by 100. So things are starting to fall into place. Okay? And very, very near 0, so for very, very small interest rates, ln 1 plus x is approximately its first Taylor polynomial, which is just x. We don't have to go any further. So ln 1 plus r over 100 is approximately r over 100, and that justifies putting it in here. And then we invert and multiply. That gets us the 69 over r that we're after. Okay? So just use 2 decimals of approximation for ln 2, and then we just use a nice linear approximation for ln 1 plus x. Okay? If you wanted more precise, you could go higher. Okay? And you could now actually adopt this and develop something like the tripling time for your investment. But that's not something that is commonly discussed in financial applications. So we just stick with our result here.